And therefore, at the beginning of Sui and Tang dynasty, the city was moved to this location and has been there since. So I grew up in Xi'an and drinking good quality groundwater, but the pumping within the city limit had to be stopped I think in the early 90s, because pumping has caused land subsidence, which in turn jeopardized the stability of residential buildings. Similar action was also taken in other major cities of China, like Beijing. So there should be another. Oh, I don't know. There's another animation didn't come up, but in California, land subsidence is also a major issue associated with groundwater withdrawals. So Governor Jerry Brown signed a Sustainable Groundwater Management Act in 2014, which requires local government and agencies to balance withdrawals with recharge. So information and any data set on renewable groundwater should help to develop strategies on sustainable development of groundwater. Oh, it was here. I didn't see it. So in terms of monitoring groundwater, there are only a handful of groundwater monitoring networks around the world. In many countries, groundwater observations are either not digitized or centrally stored. And very often, they're prohibited for public release. Even within these networks, a lot of wells have short or discontinuous records. And for instance, at the USGS website, there are only more than 1,000 active monitoring wells. And that is a very small number compared to let's see, the rain gauges we have in this country. And in addition, groundwater observations, water wells can be influenced by pumping or injection, which makes it hard to interpret observed changes. So the bulk of my talk will be on our effort to assimilating GRIS data into the catchment model for groundwater estimate for groundwater and for drought monitoring. The catchment model simulates water storage changes at 3 subsurface water stores: a surface layer, and then the root zone, and then the entire catchment profile. The model does not simulate water table variations, but groundwater storage can be estimated by subtracting water stored in the root zone from that of the entire catchment profile. Currently, the model does not simulate groundwater withdrawals, which will be an issue when with GRIS data assimilation. I will touch on that later on. So the benefit of using a land surface model for groundwater estimation is the ET estimates, which are constrained by both energy and water balances. And also the seasonality of ET is constrained by the climatology of observed vegetation coordinates. Because all models have uncertainties, so we use the data derived from the gravity recovery and the climate experiment satellite system to constrain the model estimates. The GRIS system consists of twin satellites which were flying in formation. So when the gravity changes, the distance between the twin satellites changes as well. So the satellite ranging data can be used to estimate gravity fields through inverse modeling. And then the temporal variability of gravity is mostly associated with torrential water storage changes, which include soil moisture, groundwater, snow, and surface water. So obviously, what's attracted to us is its ability to detect deeper water storage changes. In terms of drought monitoring, GRACE data, GRACE was sensitive to water storage changes throughout all seasons, which is different from satellite observed vegetations, which may not provide useful information for drought monitoring during the non-growing season. So GRACE was decommissioned late last year, and GRACE follow-on was launched this year in May, and data collection started in October, but we have not seen any data from the new mission yet. So we use an ensemble Kalman smoother to assimilate GRACE data into the catchment model. Because GRACE data are monthly observations, so it takes 2 iterations to assimilate one observation. During the first pass, the monthly mean of model simulation is calculated, and then the second pass, the increments are calculated and applied to the model states. The animation here shows, the downscaling ability of the smoother. The GRACE data that we used was provided from UT Texas, University of Texas at Austin, and it has a posted resolution of ½ degree, but the effective resolution of GRACE data is still around 150,000 square kilometers. GRACE data assimilation also enables temporal downscaling and vertical disaggregation, and it also enables gap filling, which is filling gaps when GRACE data are not available. This is very useful during the current the transition period from GRACE to GRACE follow-on. So to look at how GRACE data assimilation impacted model estimates from a higher level, we calculated the temporal standard deviation of monthly precipitation, TWS from the open loop, and TWS from the GRACE data assimilation, and the GRACE observed TWS. So we can see that open loop estimates show very large interannual variability in the tropics and in the high latitude regions, where precipitation also show larger interannual variability. GRACE observed TWS show similar spatial patterns, but with much smaller magnitudes. So data assimilation lowered the interannual variability. If we zoom into to Central Africa, we could see that the model overestimated torrential water storage during this wet period. This could be because there's errors in the forcing precipitation data, but it is more likely associated with a deficiency in model physics. For instance, the model may have underestimated surface runoff, and so that's why the higher TWS values. This behavior is kind of expected because most land surface models were only tuned to match the mean annual runoff. So when the conditions deviate more from the average, they may not perform well. But we see that data assimilation did what it's supposed to do, and to put the model estimates somewhere in between the open loop and the GRACE observation. So the ability the ensemble smoother depends on the model physics to vertically disaggregate observed TWS changes into soil moisture, snow, and groundwater. And for that, so we need independent data to validate how gray state assimilation impacted groundwater estimates. So we followed these 3 rules to select in situ wells. First of all, the water levels have to show seasonal variations, which would suggest that the wells are located in unconfined or semi-confined aquifers, where the groundwater where groundwater interacts with precipitation and ET, and that's what the model simulates. And then second, because the model does not modeling the groundwater withdrawals, so we exclude those wells that show signs of pumping or injection. And finally, because gray data are anomalies, so they have the largest impact on the interannual scale, and therefore we want to have longer observations so that the statistics we calculate are more reliable. So these are the wells that we selected following the 3 rules that I just mentioned. With the only exception is for those located in the North China Plain, where groundwater withdrawals for irrigation are widely practiced. So most wells are affected by pumping. So we included them as long as they also show seasonal variation. In order to convert water level measurements to groundwater storage, we need specific yield, which is not provided with well data. So we estimated them whenever possible using aquifer information, or at the last resort, we just extract the values from a global data set used by the PCR Globe WB model. So here we look at the impact of gray state assimilation on the regional groundwater storage. So we averaged the estimates of groundwater from the in situ source or from the model over all wells in a region to get the regional groundwater storage. So on the left, it shows that gray state assimilation reduced the estimation error in all but one region. But its impact on correlation is kind of mixed. In fact, gray state assimilation lowered the correlation in 6 regions. And this is actually consistent with the nature of a Kalman filter, which only aims at reducing estimation errors. So correlation is never explicitly warranted by the Kalman filter. But on average, we do see that gray state assimilation reduced the RMSE and improved the correlation. So this is the regional groundwater storage in Uganda, where we have 11 wells. This plot here is the terrestrial water storage estimates for Central Africa that we saw earlier. So the behavior of groundwater storage is very consistent with that of TWS, and therefore when gray state assimilation reduced the dynamic range of TWS, it also reduced that of groundwater storage, which is corroborated very well by the in situ data, which in situ data are represented by black asterisk here. And again, here is in Pennsylvania, where the open loop estimates already have a very strong correlation with in situ data, but the gray state assimilation further improved it and also reduced the estimation error. This is an example where gray state assimilation reduced the correlation, but did not improve the correlation. Reduced the estimation error, but did not improve the correlation. We suspect that this is because the cyclic phase of the model estimate is not aligned with that of the in situ data. So So when the estimation error reduces, and there's just no guarantee the correlation can be improved. If the phases were aligned, we could see that the correlation. As I mentioned that the model does not simulate groundwater withdrawals, which were detected by GRACE. And so here in the lower panel here, GRACE TWS did show a persistent, decline, which is not observed in the open loop estimates. And therefore, so GRACE data assimilation did induce a decreasing trend in both TWS and also groundwater storage estimates. And that was enough to bump up the correlation considerably. However, the simulated groundwater storage does not resemble that of in situ observation at all. So GRACE data assimilation didn't really help much here. And I forgot to mention, this is the plot out here is for North China plant, where we have 50 wells. Here we are looking at the impact of GRACE data assimilation on point scale groundwater estimates. So each panel here is a country, and each black dot represents a well. The X and the Y axis represent the difference made by GRACE data assimilation in RMSE and correlation, respectively. So we do see GRACE data improve the correlation. The negative value in X-axis represent improvement. So the improved estimation error, reduce the estimation error at most wells, but its impact on correlation is less predominant, which is consistent with what we saw with the regional groundwater storage. But we do see a positive correlation between improvements in correlation with and the decrease in root mean square error, which is it's good because it shows that the improvement in correlation is driven by reduction in estimation error, inconsistent with the nature of a Kalman filter. The reason why the coarser scale GRACE data can be useful for was able to improve point scale model estimates is that some of the model behaviors, like responding to increase in precipitation, is associated with model physics, and therefore those behaviors are regional. Okay, so the conventional wisdom is that if you improve terrestrial water storage estimates, you should also improve flux estimates, and then further to improve the water budget. But that's not true. Almost always not true for assimilating landscapes. We use the Central Africa plot as an example. As I mentioned, that overestimation of TWS during this period is also maybe caused by underestimation of surface runoff. When GRACE data assimilation reduced the TWS, it would also reduce the runoff and ET estimates. It's actually, so you're going opposite. And that will result in a smaller water budget compared to that of the open loop. So the right, this figure here is just the mass imbalances relative to precipitation. You can see that GRACE data assimilation always led to a mass imbalances. So if your application requires budget closure, GRACE data assimilation may not be right for you. And this is not unique for GRACE data. If you assimilate soil moisture, you will get the same result. And the root cause for this is because there's no constraint on flux estimates. So one of the objectives of this project was to apply GRACE data for monitoring groundwater drought. So we define groundwater drought as below average groundwater storage, and we identify that using percentiles. The percentiles were created by ranking groundwater estimates from the GRACE data assimilation against a climatology generated using model simulation based on a long record, a 67-year data forcing data set. We also applied scaling factor to make sure the GRACE data simulation run and the climatology run are consistent in terms of temporal variability. This figure here shows is the groundwater drought index map for June 23rd, 2014. So the drought in the U.S. West and Brazil were associated with long-term below average precipitation, but the events in Turkey and Shandong of China are only lasted for about a year, and these regions are frequently impacted by drought. In part, is due to the precipitation seasonality. For instance, in Shandong, where most precipitation occurs in the summer months, so lack of shortage of precipitation means more sunny days and higher temperature, and which would favor more ET and less recharge. So so drought condition can propagate very quickly to agriculture drought and groundwater. So this is just we want to look at the temporal scale of our groundwater indicator. And so we calculated the correlation between our groundwater with SPIs at different time intervals, and then we found out where they have at what month they have intervals they have the largest correlation. And so we can see that our groundwater indicator mostly correlates strongly with the 12-month SPI in most of the land areas, but it correlates strongly with short-term SPIs in the tropics. And the opposite is true for the high latitude region, where the evaporation is minimum, and therefore groundwater can develop longer-term variability. Groundwater response time can also be impacted by subsurface hydrogeological conditions, such as depth to the water table. The model does not assimilate water table variation directly, but the bedrock depth, which is a model parameter, can mimic that effect. So we can see that in the grid plains where the bedrock depths are deeper, and their groundwater has correlates strongly with longer-term SPI. But this effect can be superseded by climate condition. So this is why in Central Africa, where groundwater bedrock depths are deep, but groundwater still correlates strongly with 12-month SPI, and that's because more frequent recharge. So now we switch gear a little bit to talk about recharge. Recharge tells you how much, when, and where water enters the aquifer. So it provides different information as groundwater storage, which is just describes the current state. In the field, the recharge can be estimated by looking at the vertical distribution of groundwater age, or by measuring the profiles of injected chemicals. These methods can only be carried out in arid or semi-arid regions. And you only get a bulk estimate, like millimeter per year. There's no temporal and spatial variability. And more importantly, these methods carry great uncertainty themselves. So, so we turn to land surface modeling again for estimating groundwater recharge. We recently developed a Western States land data assimilation system, which is funded by NASA Western Water Application Office, WLDAS, to provide data for the Western states, water data for the Western states. So the WLDAS covers the area of west of the Mississippi River, and it's anchored on the NOAA MP model, which has a 2-meter root zone and a simple groundwater module. We configured a model to run at a 1 kilometer resolution to accommodate the complex terrain of the West, so that we can, and also we can integrate high-resolution forcing data and the snow observations. So this is the recharge. So hold on, back up a little. So the model does not provide a recharge. But we can estimate it by summing up the groundwater storage changes with base flow, and since we have over a time period. Since we have a daily output, so we calculate a monthly recharge. And this is just this figure here shows the mean monthly recharge based on a 38-year model simulation. And we see that most recharge occurs in the Pacific Northwest or mountainous regions, and during winter and early spring months. So these estimates represent what we call the dispersed recharge, and so they don't consider preferential flow or focused recharge associated with surface ponding or groundwater lateral flow, which can be a significant source of recharge for aquifers located near the mountains. Technically, recharge can be negative. That would represent, groundwater being lifted up into the upper soils for evaporation. But we see very little negative values, and that's because the NOAA MP model does not have the physics to lift water up. So the aquifer is actually only passively receiving recharge from the soil layers. And this is just to look at the seasonal cycle of recharge, precipitation, and ET at those 9 basins. Just like what we saw earlier, and so most recharge occurs in early spring and the winter months. And for in the drier basins like Texas Gulf, Rio Grande, precipitation occurs in the summer months, and they all goes to evaporated, so there's not much recharge at all. And this is just a look at the interannual variability of recharge and how it is affected by precipitation and ET. And this is just to show you the advantage of using the land surface model for estimating recharge, and that is you can do climate-related studies analysis. So we also evaluated on the NOAA MP estimated groundwater against the in situ data that we saw earlier. And the first thing you notice is that the estimates from the NOAA MP have very small dynamic range than the in situ data, which is just the opposite of the catchment model. And part of the reason is because groundwater is not being pulled up for ET consumption, and therefore groundwater storage remains high even during the drought events. And however, in general, the model has a good correlation with the in situ data, including the seasonality. And this is just comparison with the GRACE data. So in the Texas Gulf, Rio Grande basins, we do see that the model estimates did not reach the lower values observed by GRACE data. And that in part is because of lack of feedback from the groundwater. And this, it may also be due to the model is now simulating groundwater withdrawals. So we're going to do GRACE data simulation in the next phase, GRACE data simulation into the NOAA MP in the next phase of this project. So to conclude, land surface models provide a very useful alternative for estimating groundwater storage and recharge. This data can be useful for drought monitoring, climate analysis, and the sustainability studies. Because these models were not calibrated using in situ groundwater data or groundwater, and also they don't consider complex subsurface hydrogeological conditions. So they mainly reflect climate conditions. And then second, GRACE data simulation was very, as we have seen, GRACE data simulation was effective in constraining the temporal variability of groundwater estimates by the catchment model. The effectiveness of the GRACE data simulation may depend on model physics and the model configuration. The catchment model only has a 1 meter root zone, so that means groundwater probably contributed more to the dynamics of terrestrial water storage, and therefore GRACE data simulation was effective. We've seen that GRACE data simulation alone just cannot fix the problem that the model did not have a groundwater withdrawal modules. The challenge of implementing groundwater withdrawal, groundwater abstraction in the catchment model is that it has a very limited capacity for water, which does not allow simulation of groundwater withdrawals over extended periods. And then finally, the data will be available at a GESDISC, so we encourage you to analyze them, use them, and would appreciate your feedback. Thank you.
Okay, I wonder how many years of data you have over California for the groundwater?
For the groundwater, we have 38 years of
38 years, right? Did you find out any relationship between the wildfire frequency with the groundwater? I mean, any cause and effect things?
No, we haven't analyzed, no. We have not analyzed that.
So your result indicate that when you assimilate the GRACE data properly, you actually get a worse balance, water balance, right? So where's the most error come from? Is it mainly come from precipitation, or is it from the fact that you don't have enough physics in the land surface model?
That result actually suggests most model error.
I see. Okay.
I will go back to some people will say, oh, you improve. The only time that assimilating GRACE can improve the water budget is you assume that all the errors come from precipitation. So you can, and also the model can properly allocate these errors to the states and the fluxes. So, right, then when you assimilate the GRACE, you can improve all of them.
So there are regions in which you even has the best precipitation estimate, you still couldn't get the right balance, right? I mean, that's where you're, okay.
Exactly. So I do think the errors in the model physics is the predominant source of uncertainty.
Mainly because you don't have enough deep aquifers in terms of
it's because we never calibrated. against any TWS estimates or groundwater estimates. We never do that. So the models are just calibrated against the mean annual runoff.
Oh, okay. But there's no way you do that calibration into the model before you assimilate the GRACE data in order to get more consistency?
We could do it, but the point is calibrate. Well, first of all, we don't have so much in situ data.
Right. Yeah.
Calibrate, and then what do you do for
Right.
areas that you don't have in situ data? So, and that's, you just have to use satellite observation, which have the, the spatial and temporal coverage to influence the model estimate.
Yeah. Also, you need to have the validation data and the GRACE data. You don't want to put them all together, then you have no validation. Yeah, that's the dilemma you always face with data assimilation. How much you want to assimilate, how much you want to leave as validation.
It's never easy to pressure or groundwater data, and in fact, what we learned from the groundwater community is that you shouldn't do it. You should not do the calibration.
So do you verify only against wells that are not influenced too much by human beings?
Yes, so that when we select the in situ wells, we look for signs of influence of pumping. Like if the wells have been affected by pumping, they show sudden, jumps or drops. So we always look for that. If they have been, if we think they have been influenced by pumping, then we will not include them. Because the primary reason is because the model currently does not simulate freeze drought.
I'm a little surprised that your correlation is high for 12 months, as opposed to, say, a much longer time scale. I thought that some of these aquifers recharge over hundreds of years.
Oh, yeah.
So what am I listening to here?
Well, this is model estimate. This is what a model estimates show. So the model, the groundwater, is showing strong correlation with 12 months SPIs, but the in situ data may be totally different. You're absolutely right. In some drier areas, water table.
Okay, so I think that's it. Let's thank the speaker again and conclude.